Hey guys, what's up? This is Vale and welcome to my channel. Today I'm going to be here for a very short span of time but discuss something very interesting. I have wrote a little code on C which I'll explain and also provide you with a code that you can actually do something very interesting, which I'll show you on my computer in just a few moments. Now, the reason I'm doing this is because I was just researching about a new attack vector called return to libc attack, and that is a very interesting kind of attack that you can do instead of buffer overflow shellcode style attack. But in case we actually do the actual buffer overflow, but we do not have a shellcode with us because there are something called no execute stack or something called data execution prevention system. So that's how the stack remains protected, so we cannot actually attack with a shellcode in which the return to libc scenario actually works. So I was researching with that and I encountered a bug in my program that when I was actually overflowing, the stack frame actually somehow completely deleted the saved EIP or the saved instruction pointer address, and neither it was overflowing and there was nothing in place where the saved instruction pointer should be. There was nothing. So I was just studying that and I was thinking that if there was some way where a student who is new to this topic, who doesn't need to be, a cybersecurity researcher or a red team tester, so someone who is just, interested in knowing what happens exactly in a computer, what happens in the stack, what happens in the heap and stuff like that. So if there was just something that a normal student, an average Joe, can actually see the same thing but without the knowledge of reverse engineering or debuggers or assembly itself. So I researched a lot about it and found a topic which is very interesting, and the most interesting fact about it is that not many people actually knows that it even happens. So when I was researching about the topic myself, there was not a lot of videos or instructions on the internet, only some documentations which I shouldn't term as exactly easy. So it was quite complicated to exactly get what you want from just the documentation. So the thing which I'm talking about is we can actually do real assembly. We can take control of the CPU that we have exactly as we want. So the kernel won't actually decide what registers to use or what memory areas to use or access, read or write. We can do that manually by ourselves by writing direct assembly code within our C program. So I have developed this little C program that has I guess 10 to 15 lines. That's it. So if you actually include that in your test program where you want to see how the stack works, or you are just writing a sample buffer overflow program to practice on, if you actually include these codes, you will see that within the program you can actually see the whole stack frame without actually using a reverse engineering tool or something called a debugger, which you probably already know if you have been watching my videos. For example, you have a simple program of addition. So if you actually run the program with my codes in it, the addition program will happen, but you will also get the information about the current stack pointer, information about the current base pointer, information about the old saved instruction pointer's address, and also all of the contents within the stack in hex format. So everything can be done with a decompiler or a debugger such as a GDB or IDA Pro or something like that. So that can be done with those tools. But if you are not OSCP aspirant or something like you want to be a hacker or a cybersecurity researcher, if you don't want that, you are just curious about what happens in a stack without actually using those tools or learning how to use those tools, my program will just do great for you. So the program is itself very interesting. So I'm going to show you the 15 lines of codes that I have wrote, and it's really very beautiful. So I'll see you on my computer. Bye. Okay, so here is the code that I have written, and I'll just try to explain line by line. And the main lines that we are actually concerned about are these 1, 2, 3, 4, 5, 6, 7, these 7 lines and these 4 lines right here. So the goal of the program is to somehow view the stack frame without using a debugger or a disassembly software. So what we want to do and what we need to see for our stack frame is some of those registers, such as the stack pointer, the base pointer, the old saved instruction pointer's address, the old saved base pointer's address, and the content between the stack pointer and the base pointer. And that is what the whole program is doing right here. So if you have a practice code for a buffer overflow or a practice addition code or whatever it is, you can just copy from here to here and you can see the stack information for any program written in C with these respective lines. So I'll just try to say what I did here. I have taken some variables of the type long integer and one unsigned character called data string. So now I'll just explain why these exist and the context of these being actually present. So the syntax for writing assembly within the C language is simply just by typing ASM and 2 brackets. That's all you need to perform assembly instructions within the C language. So anything you write within these ASM keyword is going to perform a direct assembly instruction as instructed by you. So you know errors from these parts of the code will not be actually compiled by the compiler. So you will not actually get errors or warning messages from the compiler. You will get the errors from directly your CPU, which means the code will not work or the code will directly crash. You will get a SIG-IL or a SIG-SEV. So anything you can get, you will not get it via the compiler, because the codes of the instructions within these brackets is basically you are directly telling your hardware to do stuff for you, which the C languages or higher level languages do automatically, that is written in the compiler. So this is the basic syntax of writing assembly within the C language, and now I'll just explain what I did here. So first of all, if you have noticed that I have the AT&T syntax right here, but if you have been seeing my videos, you already probably know that I am much a fan of the Intel syntax. Now we could have done the Intel syntax here, but the problem is I have already learned the AT&T syntax first before actually coming to know that we can do the same with Intel syntax by writing something called like a prefix Intel, something like that. So as I have already learned the AT&T syntax, so I just did it with AT&T syntax. So anyways, first of all, if you notice the assembly code here, in AT&T syntax, to address a CPU register, we just need one particular percentage sign. So why there are two? Now the reason being, when we actually give 2 percentage signs in these instructions, that means that we are actually going to manipulate the values right here. So for example, if I suppose say if I have a variable called a and that a has a variable called 10, now what I could have done is just directly say that move 10 and comma maybe EBX. So the value 10 will directly go to EBX, but what if that 10 is a variable? So say that a was 10, so on the next cycle maybe a is 12. So how can I take the value from the variable a and put it in one of those registers? So to manipulate these registers, we need to do 2 of those percentage signs, so we can do these things after that. So for example, there is an equal sign here that you can see. This specifically means output. So if I don't get confused right now because I'm going to explain, but here we have just written output, but if I actually wanted to say have an input, so if there was a variable called a, maybe say int a, that is a variable equals maybe say 10. So if I wanted the value of a to go to EBP, which in this case I didn't do, but if I did wanted to do that, what I needed to do was simply just say maybe this is EBX, so I need to write B, and then I should have done something like A. That's it. Now why I did write B here, it has a specific reason for that, but just for now notice that what is basically happening is we are actually manipulating the EBX register by not literally giving it a value, but manipulating the compiler to take what is in the variable A to go to the register called EBX. So for manipulating these registers, we need to give 2% signs. So in this case, the output will also be kept in the EBX register, and the input is also going to be taken to the EBX register. So this might encounter an error, but if we wanted to do that, we can actually. Now if I just explain the code as it was before, what I was doing is simply first taking the value of the base pointer, which is, in this case, this is all 32-bit system. So in case of 32-bit, we already know that the base pointer is going to be EBP, or the stack pointer is going to be ESP, or every registers we should address with the prefix E. If it was 64-bit, this should just change to RBP from EBP. That's it. We don't need to know any more than that. So what I'm doing is moving the value of EBP to EBX, and I'm also keeping the value of the EBX onto EBX. Now the reason being, here you can see there are B, there is A, there is A, there is again B, and there is A, which this means is basically, in case of inline assembly, which is also this type of programming is called for. So in an inline assembly code, A stands for EAX, B stands for EBX, and as well as C stands for ECX, D stands for EDX, a capital letter D stands for the EDI, the capital letter for S stands for ESI. So that's how these A, B, C, Ds work here in inline assembly. So when I'm writing equals B, that means that we are particularly mentioning the output. So this command basically means that you must keep this variable within the register EBX, and also the result of this calculation will be kept in EBX. So when I'm moving the value of EBP to EBX, that value is going to be kept to EBX itself, and we are just going to get an output to this variable called BP underscore address. So EBP's value went to EBX and also stored in EBX for now, but in the meantime we got the value of base pointer address, which is a variable right here. So now BP ADDR, or the base pointer address, this variable has particularly the value of EBX, which we just moved from EBP to EBX, which means BP ADDR currently has now the value of the base pointer. On the next line we are doing the same, but only with one exception, that in this case, if you remember that EBX now currently holds the address of EBP. So now what I'm doing is we are moving whatever is it at the address that is pointed by EBX right now, which means basically it's EBP, because we moved the address of EBP to EBX, and that address is currently holding some other information on the stack or on the memory, right? So from Intel syntax, when we wanted to reference a memory operand, we used to give the square brackets, but in AT&T syntax it's the round brackets. Okay, so move whatever is it in the address contained by EBX to the register EAX, and in the meantime store the result into EAX, which shall be casted to the variable BP deref, or I meant it as the dereferenced base pointer, because if we remember from the stack frame video that the current base pointer is holding an address, and that address we want. So if the base pointer is holding the address 100, so on the first line 100 will be copied to base pointer address, and on the second line it will fetch whatever it is at the address 100. So in that case, if the address 100 is holding the address or the information, maybe say 95, so in this case 95 will be copied to EAX, and that shall also be outputted to EAX, and that value is casted to base pointer dereferenced. So we just kept those values into both of those variables, and on the third line what I'm doing is I'm adding 4 to EBP and then copying the value to EAX. Now if you remember why exactly I am adding 4 to the base pointer's current value, the reason being, if you remember, the old saved instruction pointer in case of 32-bit is just the next value on the stack in the reverse order, which means that when a function actually starts, you already know that the instruction pointer is first saved or pushed to the stack, and then the old base pointer is pushed, right? So just below the base pointer is the old saved instruction pointer, and that can be referenced as EBP plus 4. So that is what exactly is happening here. I'm adding 4 with EBP and keeping that value into EAX, and that value is again stored into EAX, and here it is casted to the variable calc ADDR. Now I just taken this variable as a pawn variable just to see in the printf that if it actually indeed added 4 to EBP. On the fourth line, you can see that we are moving whatever is at the address that is currently being held by EAX, move that address to EBX. So if this was just EAX, the value of EAX would be just copied to EBX, but in this case we have a round bracket. That means whatever is it at the address that is held by EBX is transferred to EBX. Now what is at EAX right now? If you remember, in the previous instruction, we added 4 to the base pointer, and then that address is being kept to EAX. So if, for example, if the base pointer was 100, then we are storing 104 onto EAX, and on this line we are dereferencing the address 104, which means we actually want to keep in this register whatever it is at the address 104, and then again put that value or the result within the EBX register itself, and in the meantime cast that value in the variable called the saved IP, or which I meant to be as saved instruction pointer. So on the next line we have no relation with these anymore, so I'm just doing the same thing as base pointer. If you remember that on the first line I have just taken the value of base pointer to EBX. Here I am doing the same thing, but this time for the stack pointer. So I am simply moving whatever it is at the stack pointer register to EAX, in the meantime also keeping the value in EAX, thus casting the value out to the SP or stack pointer variable. This line, if you can see, it's a little bit different. I'm just simply moving whatever it is at EBP to EAX, just like that. In this case, we are not taking an output or giving it an input, which means these EAX and EBP variables are not manually manipulated by the user. So one percentage sign works perfectly. If I actually wanted to manipulate this with an output or an input, then I should have given 2 percentage signs, but in this case it's just a simple assembly instruction to say that move whatever it is in EBP to EAX. So 1 percentage sign suffices, no problem in that. So we are moving whatever it is at EBP to EAX, and in this line I'm doing something special. If you can see that there is a subtraction instruction, which means I'm subtracting what is at ESP from the value EAX. Now if you see the previous line, currently the EAX register has the value of the current base pointer. So in this case what I'm doing is I am subtracting the value of ESP from the value of EAX, which basically holds the address for the current base pointer. So which means the value of stack pointer is actually deducted from the value of base pointer, and the remaining, the value which is the result of a subtraction is casted out, or is kept on the EAX register and casted out to the variable called diff. Diff means basically difference. So all of the lines, that basically means is that on the first one line I'm just simply taking the address of the base pointer. On the second line I'm trying to dereference what is it at the address held by the base pointer. On the third line I'm trying to calculate the value or the address for the saved old instruction pointer. On the fourth line I'm simply dereferencing what is it at the saved instruction pointer. On the fifth line I'm simply taking the value of stack pointer to the variable SP, and on the fifth and sixth lines I'm calculating the difference between the stack pointer and the base pointer. And I'm calculating the difference between the stack pointer and the base pointer is because the contents of whatever it is between the stack pointer and base pointer is basically the contents of the stack. in these lines you can just simply see I'm printing out the information. So the current value of stack pointer is printed out, the current value of base pointer is printed out, then whatever it is at the base pointer is dereferenced on this line, whatever it is at the saved old instruction pointer's address is displayed right here, and the size of the stack frame is basically the difference between the stack pointer and the base pointer, which is displayed right here. On this loop, what I'm simply doing is just printing out all the values starting from the base pointer towards the stack pointer, each of them byte by byte. So if you see, for example, I just created a loop right here, so I is initiated at 0 and it's conditioned to be lower than difference, which is the size of the stack, and then incremented I by 1. In here you can see that I am basically moving the value of I to the register called ECX. In here you can see that I have both given an output and an input. So you can pretty much see that I just took the value of I, which is going to be changed each time the loop goes on. I'm taking the value of I and putting the value of I to the EAX register via this input segment. So you can see from this line that I simply have two segments here as output, as one as input. So when actually EAX is moved to ECX, that result is also kept at ECX and in the meantime casted to the variable called counter. And in case of EAX, I'm manually putting in the value of I into the EAX register. So I think you are a little bit confused on this line, but just check it out simply. I am basically moving whatever it is at EAX to ECX. Now what EAX will have is decided right here. So at the EAX register we will have the value of I, which is going to be varied each time the loop goes on, and for the output we will have the register ECX, and that will be casted out to the counter variable. That's it, nothing more. So on the next line we are just simply moving whatever it is at the stack pointer variable to EBX and keeping it in the EBX variable which we manually took here, then adding the ECX with EBX. So if you remember, if you see that ESP's value is now stored on EBX, right? So the stack pointer is now at EBX, and on each loop I'm adding the current value of ECX with the stack pointer's value, which currently is in the EBX register. So for a dry run, if you see that when I is 0, then 0 is added to the EBX register's value. On the next loop, 1 is added to the EBX register's value. On the next loop, 2 is added to the EBX register's value, and in the EBX register we simply have the value of the stack pointer. So basically what I'm trying to do here is I am incrementing the value of the stack pointer. So if the stack pointer was say at 116, then on each loop we are referencing the addresses 116, 117, 118, 119, 120. So we are just keeping in the values, and on the end of the loop I'm basically dereferencing from this line here whatever it is at that current memory frame. So for example, when the stack pointer is at say 116, so on 117th memory address there should be some value, right? On the 118th address there should be some value, on the 119th address there should be some value, and we are simply dereferencing that. So if you can see that when the addition is going on, the output is still kept on the EBX register, right? So that output, say that output is now, say that I's value is currently 1, so ECX will have the value 1, EBX should hold the value of ESP, which say is 116. So 1 is added to 116, and that 116th value is now kept on the EBX register, and on the next line I am dereferencing the 116th memory address and keeping the dereferenced value in the register EAX, and also casting that out into the data underscore str variable. And on the next line I'm simply just printing out the hex version of whatever it is at that current memory address. So this is going on every cycle of the loop. So if I just run the program, you'll see Okay, so let me just run GDB. And just run the program. Okay, there is some problem. Okay, so now let me just say run to see if the program works. Nice. So now let's check line by line what happens. So break main, and I'll just say run. Next instruction, let me just, for example, print out the value of ESP. We can see that the value of ESP in our current stack frame is FFFF D2B0. If I do the same for EBP, we can see that the current value is FFFF D2F8, and whatever it is at the saved instruction pointer's address is, we can reference it as print EBP plus 4. Okay, there is some problem. So 4. Oh my god, numlock is not working. EBP plus 4. Nice. So you can see we have the address called D2FC, and whatever it is at that address, if we want to see, we can just go on and say EBP plus 4. What? Okay, sorry. We can see that we have this address right now. So if I just remember, this is the value of ESP, this is the value of EBP, and this is the value of the saved instruction pointer. Also, we can do the same by typing in info frame. We can see that we have the saved EIP as F7DF1EF1, which is the same as F7DF1EF1. So if I just let my program run and let me check. Okay, you can see that the stack it is saying that the stack pointer is pointing to FFFFD2B0. Now, is it right? Let me check. FFFFD2B0. It's right. So the stack pointer's address from GDB and the stack pointer's address from my own program is perfectly a match. Then for EBP, we have FFFFD2F8. So if I continue running, FFFFD2F8, it's perfect. And okay, BP holding saved address nil. So if I just go on and watch what is it at the address of EBP, if we dereference it from GDB, so again EBP, if I do that, you can see that we are getting all zeros. So there is nothing currently pushed on to the location of EBP right here. So, and let's go on a few lines, and you can see that the saved instruction pointer is F7DFE1F1 is the same as the saved EIP, which is F7DFE1F1. So that was the main thing of my program, and the last thing that is remaining is the difference between stack pointer and the base pointer, or the size of the stack frame. So if I just go on a few lines, we can see that the size of the stack frame is 0x48. So if I just copy and paste some values and I try to find out what is the decimal value of this number, we can try to see it. So hex, okay, I'll just type it 0x48. So I'm getting, we have the value of 72. So if I just go ahead and say xbx 72 times from ESP, so if I actually do that, we are getting these values, right? So if I just let my program run, let me check what happens. So if I just press continue, you can see we have the same things right here. So 0 0 0 0 0 0, then we have 30 FB F7. Here also we have 30 FB F7. Where is the F7? So I think there is some errors in this part. It worked yesterday completely fine, so maybe I'll try to fix that in my code. But this is the general idea. I don't know why it didn't work today. It worked every time yesterday when I was testing the code out. So I guess I'm sorry for that, but I'll try to definitely fix in my code. I'll just upload my code to one of my Reddit pages, and I will link that page into this video's about section, so you can also try and fix that for me, and share it with all of your friends, really interested computer science students. So I hope that is going to be the end of the video, and thank you, goodbye. I'll come up with the red tulip C tutorial soon enough. I was just trying out this code, just out of curiosity and as a hobby. It was nothing very serious of me. So thank you. This is the end of the video, and goodbye. See you next time.